So you've got this beast of a gaming PC, right? A machine that can render entire universes in stunning detail. But have you ever stopped to wonder why that same powerhouse sometimes stumbles over what seems like the most basic math? Well, today, we're going to peel back the layers and find the ghost in the machine. It's that classic, super frustrating moment. You're in the zone, everything's perfect, and then, bam, your character is suddenly snagged on an invisible wall. Or maybe some random object starts vibrating like crazy for no reason. This isn't just a random bug. It's often the result of a really deep, fundamental disconnect between how we see numbers and how computers actually work with them. Now, to really get this, we've got to clear up a super common math confusion first. When we see a negative exponent, like 2 to the power of -3, our brains almost always want to jump to a negative number, like -8. But nope, that's not it at all. That little minus sign isn't about making the number negative, it's telling us to do something completely different. It's about direction. It's telling us to take the reciprocal, basically to flip the operation. So instead of multiplying 2 times 2 times 2, that negative sign means we do the inverse, 1 divided by 2 times 2 times 2. See? So 2 to the -3 isn't -8, it's 1/8. The big thing to remember here is that a negative exponent is a signal for division. You know, there's a really beautiful logic to math. It all starts with the simplest thing, addition. Now, if you do addition over and over again, what do you get? Multiplication. And if you repeat multiplication over and over, boom, you get exponentiation. It's like a ladder where each rung is just a more powerful version of the one below it. And for every single step you take up that ladder, there's a matching step to go back down. The opposite of addition, subtraction. The opposite of multiplication, division. And so it just makes sense that the opposite of exponentiation is taking the reciprocal. This is exactly why a negative exponent means division. It's just the other side of the coin. Okay, so we've got our math straight. But what in the world does this have to do with computers and those annoying game glitches? Well, it all comes down to what happens when a computer, a machine that only thinks in ones and zeros, tries to understand a simple decimal number like 0.1. Think about it. We have 10 fingers, so we use a base 10 system. Computers only have 2 fingers, 0 and 1. So to make fractions, they can't use tenths or hundredths like we do. Their entire toolkit is built on powers of 2. Halves, quarters, eighths, sixteenths, and it just keeps going. Those are the only building blocks it's got to work with. So let's try this. Let's see what happens when a computer tries to build the number 0.1 using only those blocks. A half is too big, a quarter is too big, an eighth is too big. So the first piece it can use is 1/16. That gets us to 0.0625. Okay, we've started, but we're obviously not there yet. All right, let's add the next smallest piece it has, 1/32. Now we're at 0.09375. We're getting really close, but we're still not exactly there. And here is the absolute most important part. No matter how many of these tiny binary pieces we keep adding, we can get infinitely close to 0.1, but we will never, ever land on it perfectly. There's always this tiny little bit left over. And this right here, this is the heart of the entire problem. For us, in our base 10 world, 0.1 is clean, simple, and finite. But for a computer trying to build it in binary, it's an infinite repeating number that goes on forever, just like 1/3 becomes 0.333 for us. It never ends. Now, a computer doesn't have infinite memory. It can't store a number that goes on forever. So it's forced to do something, well, a little messy. It has to just chop it off at some point. It truncates it. And that cut, that's it. That's the source of a tiny, almost invisible error. The number the computer is storing isn't exactly 0.1. It's just an incredibly close approximation of it. In just one calculation, this error is so small you'd never, ever notice it. But a game's physics engine isn't doing one calculation. It's doing thousands, maybe millions every single minute. And with every single one of those operations, that tiny little error gets added to the pile. It doesn't go away. It accumulates. It snowballs. And this snowballing error creates what you can think of as a drift, a tiny gap between the game's math and what you're seeing on screen. Over thousands of frames, that drift gets just big enough to confuse the physics. The game thinks your character is a tiny fraction of an inch off from where it should be, and that's when you get stuck on that invisible wall. That's the ghost in the machine. The wild thing is, these tiny little imperfections are baked into the very foundation of how our digital world works. It really makes you wonder, doesn't it? If a simple fraction can cause this kind of drift in a video game, what other invisible math errors are humming away in the background, quietly running everything from the stock market to our social media feeds?